edge detection and is better tuned for feature extraction from a wide range of scales. This model achieves notable improvements over the baselines in region outlines and level of detail on both tasks. Okay, so that is what the abstract is saying. So now let us go into the, or let us briefly go over the various details of the paper. Okay, so first there is a description of the data set. So the data collection was carried out with a helicopter flying over the greater area of Munich, Germany. So as you, so this data set was taken not from us from remote from satellites, as will be more like most of the remote sensing like is based on like will be based on satellite imagery, but so in this case, of course, they are doing it with, say, a helicopter collected data. Now, but that is also useful because in those regions where they are capable of doing this kind of thing, it is important to do it so that with using domain adaptation, the same models can be exported to other regions. A low-cost camera system consisting of 3 standard DSLR cameras, etc. So in total, 16 non-overlapping RGB images of size about this many pixels were chosen. So you can see how high resolution it is. Like every image has like about 5,000 cross 3,000 pixels. Okay. This distance is about 13 centimeters per pixel. So they, as they were talking about, like so like that is, this is called the ground sampling distance. So like it's like how many or what is the amount of or what is the distance covered by every pixel. So it's like each pixel or that is covers about 13 centimeters of region according to what they had these data sets. These images represent urban and partly rural areas with highways, first or second order roads, and complex traffic situations. And then there are like 31 semantic categories are annotated. So low vegetations, paved roads, non-paved roads, paved working places, etc., etc. So as I said, the labels are at multiple levels of detailing. Okay. And so like manual annotation is there. So fine. Mm. Okay, so and here are like they have actually shown some statistical properties of the different classes and the and how frequent the different classes are. Okay, so that is how that is how many pixels or what is the number of annotated pixels and instances per class are available. And then, so whenever we are doing any this kind of a task, it is also necessary to evaluate them. So they have defined various metrics for evaluation. So basically we need the like something along the lines of precision and recall. That is for every like let us say I am interested in a particular class of objects, let us say buildings. So then so that I will look at the different pixels which have been marked as uh, building, and then I will try to see how many of them actually are buildings. So that is like the precision. And then there is the recall, that is out of all the pixels that are associated with that are actually associated with buildings, I mean in the ground truth data set, our semantic segmentation have been able to classify how many of those pixels as as buildings. So these are so based on this we have these concepts of true positive, false negative, etc. So based on that they have defined something like an intersection over union matrix, which is like true positive divided by true positive plus false negative. So like these are basically different variations of the standard precision and recall. So they have been they have used these for specific purposes. Now so state of the art in semantic segmentation. So like this paper they have compared, first of all, compared various existing algorithms or models, and then propose their own ones. So, so here, as the detection results have matured, reaching around 80% mean average precision on some object detection data sets, and also on some aerial object detection challenge. So now they yeah, so in recent years, fully connected neural networks or FCNs have achieved remarkable performance on several semantic segmentation benchmarks. Current state-of-the-art methods include Auto Deep Lab, Dense ASPP, and like so. So these are some of the papers which are all based on convolutional neural networks. So I'm not going into the details. So like if anyone is interested in doing a project on this matter, you should explore these papers. While specific architecture choices offer a good baseline performance, the integration of a multi-scale context aggregation module is key to competitive performance. So so each of these are specific architectures, but what they are saying is that like they need the context, that is the context of the image has to be taken into account at multiple scales. That is by context they mean the information which is already available, that is an urban image, that these are the defined object categories. So these have to be somehow integrated in their performance. Indeed, the context information is crucial for pixel labeling tasks. It is best leveraged by so-called pyramid pooling modules using either stacks of input images at different scales or stacks of convolution layers at different dilation rates, as in deep lab. So again, so like as I was mentioning earlier, in case of object detection, the objects, that is the same object can be present at multiple scales. It can be, it can cover only a small number of pixels or a large number of pixels, or maybe the entire image and things like that. So it is necessary to build a pyramid-like structure, like of the I mean stacks of input images at different scales. Okay, so that like we get something like an image pyramid. Maybe at the bottom of the pyramid we have a like a large image I mean such an image which contains the object at the across the full of it. Then we at the next level we have another image which contains the target object at only a specific smaller part, and so on. So like such the at different images at different scales, they are stacked together to as a in the form of a pyramid. So it's a an old concept in the task of this segmentation, but it can be that same concept can be utilized in case of deep learning also. That's what they mean by instead of stacking the images at different scales, it is also possible to consider the stacks of convolutional layers with different dilation rates. So dilation rates means like, so the filter of the using which they do the convolution, like this filter. So this basically what it does is it is doing a dilation of the image. So like here, as you can see that this 3 cross 3 filter, it is focusing on a 3 cross 3 that is total 9 pixels, and replacing it by only 1 pixel. That is from 9 pixel it is being dilated to the level of like a 1 pixel. So that is the larger filter will of course do like a more a stronger dilation. That is, it will replace maybe 25 pixels by 1 pixel, or maybe 100 pixels by 1 pixel, and so on. And a smaller filter will do like a less dilation. So the same thing. So there are certain things which are difficult to see in like without the dilation, but when we dilate the image, that becomes prominent, and the reverse is also true. So typically people that is why the we have different layers of convolution. That is, each layer of convolution is like corresponding to one level of dilation. So that is why it is important to build, like as they are saying, it is important to do the dilation at multiple layers. So in tables 2 and 4, so they have shown the benchmark results of various benchmark methods, and then they have themselves proposed a method. So 31 highly similar classes and small complex objects in cities in skyscapes necessitate a specialized architecture that unifies latest architectural improvements and proves more effective than the state of the art. Motivated by the major errors from our benchmarking analysis, we propose a multitask method that tackles both dense prediction and edge detection to improve the performance on boundary regions. That is, these boundaries are most crucial to differentiate between the different classes of objects. So for that, to identify which pixels form the are at the boundary of, that is, mark the boundary of one class and the that is end of one class and the start of another class. I mean, say suppose there is a building and a road next to it, so where exactly the building ends and the road starts. So like it is necessary, that is we want such edges to be, or the such boundaries to be very prominent. So for that purpose what we need is a good edge detection. The edge pixels have to be identified correctly. So they are, according to their claim, the kind of neural network they have built, they are that is able to do this edge detection properly. So they are the neural network which they have proposed that has different building blocks. So one is the FDB, or the fully dense block, where we use more residual connections compared to the existing dense blocks. So dense, as the name suggests, we like it's closer to a like a fully connected layer. That is, instead of like doing that is dense indicates the how frequent, or how, what is the number of these edges they have. So like as we saw in yesterday's example of a convolutional network, uh, say here, right? So like here, so this is a like as you can see, this is actually a sparse matrix. So many of the elements are zero. So there is a repeating structure. So apart from that repeating structure, the remaining values are zero, which indicates that like a zero value in this weight matrix basically means the absence of edges. So the input is 6 dimensional here and the output is 4 dimensional. So total 6 into 4, 24 connections can be there, 24 edges can be there. But an edge weight of 0 means that some of those edges are not there. So typically a convolutional neural network in a convolution layer is quite sparse due to the presence of lots of these zeros. On the other hand, a fully connected layer will have all the 24 connections. So here, as you can see, each of these 4 columns, they have only 3. So basically we have 12 connections as opposed to 24 connections in a fully connected layer. So a dense layer may have something in between, maybe 18 connections or so. So that is what they are considering. And apart from that, they have various other building blocks in their network. So some FRSR, which is which they are calling as fully resolution separable individual units, and some other special pyramid pooling and so on. So like again, pooling, as I said, can be done at like different pooling blocks. That is, it can be either 2x2 pooling or 3x3 pooling, 4x4 pooling, etc. So in each of these pooling blocks, I guess they do the pooling at multiple using multiple pool sizes. And similarly, they have also various other building blocks. So using all those building blocks, they build this kind of a network. So the structure might look very complicated. but the whole idea is that the input is progressively passed through a number of layers like this. And yes, and then based on that, and they also have some loss function. So like as it as should be obvious that this kind of a network, it will have like a some exceedingly large number of parameters. In fact, they have written it also here. This model has 137 million parameters. So you can understand how difficult it will be to train such an image, I mean such a network. So what they do is, so they do not have sufficient number of images for training such a detailed thing. So what they do is they crop the images, whatever images they have. So they earlier image mentioned some 5,000 cross 3,000 images they have. I mean, each image is of size 5,000 cross 3,000. But there are only 16 images like that because these are extremely expensive images. So what they do is each of those images themselves, they crop into various patches. So of size 512 by 512. Okay. And then using that they so but the pixel level annotations are possible. So like basically this way they get a very large number of, I mean a sufficiently large number of images, as they've written some 8820 training images. I'll still say that this number is small compared to the number of parameters they have got, but well, there is a limit to how much images can be procured. So well, so after this, they train the model and then they are able to do the prediction. And then they report their results. So they have that average precision, average recall, etc. For the different models which they have considered. And then they show that the best results are obtained by the network which they have proposed, the Skyscapes nets. Okay, so basically that's what this paper is about. So it is like also showing some examples that this is what the aerial image looks like. It's an RGB image, and so if you do the ground truth, I mean the pixel level segmentation, if you do that, these pixels are the roads, these pixels are the buildings, and these pixels are the trees, etc. Then this is what the ground truth segmentation looks like. While the different segmentations done by the different algorithms are shown here. So as you can see that all of them have done a reasonably good job. There is, I mean, each of these segmentations broadly agree with the ground truth, except some small differences. Like here, all the like this is the structure of the say the trees or the forested regions, and here that structure looks slightly different and things like that. But so the some like at some pixel level there might be differences between the ground truth, but overall all the methods look the similar. But they if they actually quantify the results, then they show that the Skyscapes, the proposed net, gives the best performance compared to. And then they have done some experiments, these domain adaptation experiments. So as they mentioned, they have collected their imagery over a particular region in Germany, and they have trained the image along with it. Now, I mean, they have trained their model along with it. Now that same thing, they are going to the same model they are going to run in other cities of the world, and they will see if it can adapt to these new domains. I mean, they may not have done any separate domain adaptation like for these new regions, but they may simply be using the same network without any change of the weights, because all the cities will have roughly the same set of labels. So here these are the different classes which they are showing. So this is another city in Germany, Potsdam. Then they have gone to say in part of Australia, and here they are again doing the same task, maybe using the same skyscapes. And so like as they have showed, like without any fine tuning. So they have just done some simple adjustment, but they have actually not done any fine tuning. Or I mean the edge weights they have not changed. But they can also do fine tune. That is, if, they can also do the fine tuning in which they can change some of the edge weights. So there are some papers which some works which do that. These guys have not done it. So anyway, so this is one interesting paper which touches upon the concepts of object detect not object detection. I mean the semantic segmentation as well as for the domain adaptation. The catch here is that the images that they deal with, they are mostly RGB images captured from a helicopter. I mean, the images are that is compared to the images which we see, which we have or utilize in standard computer vision tasks, that is the images captured by camera. It's the same kind of images only. The only difference is that they are taken from the top. However, the idea is will remain the same, but the nature of the images may be different when we use, say, instead of imagery, then one paper which we discussed today. Let us consider another paper. So this is called CloudNet. So this is an end-to-end cloud detection algorithm for Landsat 8 imagery. So now we have come to satellite imagery. So Landsat, this is it's a satellite which Landsat is the name of a satellite which I mean Landsat 8 is the name of the satellite which produces these imagery from all over the world, and it's available also. So like if some of you are interested to do a project on these remote sensing of these Landsat imagery, you can actually go to their website and collect the data. So what they are doing is that so when we take the so the image, the satellite are of course at a very high altitude. So the satellite imagery are often hampered by the presence of cloud. That is they are the clouds basically form some kind of obstruction. So it is necessary to identify the clouds in those satellite imagery and replace them. That is, replace them by like what lies beneath the clouds. So that is the task which they are trying to do. Cloud detection in satellite images is an important first step in many remote sensing applications. This problem is more challenging when only a limited number of spectral bands are available. So these satellites, they have a number of spectral bands. So each, like you can consider the different spectral bands as the different channels as they do in case of RGB images. Now, the number of these spectral bands, they can vary from satellite to satellite, and even within the satellite, they may vary in the certain circumstances. Now, to address this problem, a deep learning based algorithm is proposed in this paper. This algorithm consists of a fully connected, even fully convolutional network (FCN) that is trained by multiple patches of Landsat 8 images. So, in the previous paper also we talked about training you on image patches rather than entire images. The same thing they are doing just to focus on specific regions of the image. We often focus on patches of the image rather than the entire image itself, because an entire image will contain a large number of things, but we want details. So like we can actually divide the image into multiple patches, overlapping patches, and then learn to do our classification or segmentation, whatever we are doing on the image patches. Okay, this network, which is called the CloudNet, is capable of capturing global and local cloud features in an image using its convolutional blocks. So a cloud will of course have certain characteristics or certain features. I mean, global features as in the overall shape of the cloud, and local features may mean, say, the texture of a particular part of the cloud. I mean, different parts of the cloud will have different densities. So maybe some parts of the cloud will be hazy and so on. So all those things, it is like they are claiming is capable of capturing those things. That is the again the what they really mean by that is, so as I was saying, the different layers of the neural network, they basically learn different different kinds of things about the image. So and the visualization people, they try to visualize what each layer of the network has learned. So they are claiming that some of these layers, they actually uh, or learn to identify various global or local properties of a cloud. Okay, since the proposed method is an end-to-end solution, no complicated pre-processing step is required. So by end-to-end solution, what it means is that the input will be like what they need. Like a remote sensing image containing clouds, and the output will be like just the like locations of the clouds in those images. That is, they do not have to do any manual pre-processing or post-processing on the images. Whatever image they get, they will just put as inputs to the directly as inputs to the neural network, and the output will be directly the what they want. Our experimental results prove that the proposed perform method outperforms state-of-the-art art method by over a benchmark dataset by 8.7%. So so let us so okay, in recent years, deep learning based methods have been proved to deliver good performance in many image processing applications. Researchers in the remote sensing field have also proposed such algorithms to address the problems of cloud detection. For example, Zhai et al. Utilized two CNNs for classification of subregions in an image into thick cloud, thin cloud, or non-cloud. Many fully convolutional neural networks have been introduced for semantic segmentation of the images. Most of these networks have an encoder-decoder architecture which is inspired by UNet. Right? So UNet, as I have mentioned several times, like they first downsample the image and get a very condensed representation, that is called the encoding step, and from there they upsample the image and restore it back to the original like the original resolution, that is called the decoder part. The effectiveness of UNet has been proven in many other computer vision applications also. Authors in 13 use an FCN to segment the cloud regions of Landsat 8 images. This this network was a very deep version of UNet and was trained by images and their automatically generated ground truths. Just please wait for a couple of minutes. So in this paper, we introduce a new cloud detection network, CloudNet, for end-to-end pixel level labeling of the satellite images. We specifically designed convolutional blocks of CloudNet to capture complicated semantic features of clouds in remote sensing images. Unlike like this is basically what they are repeating, they said I mean the clouds may have what they like semantic features which they are claiming, like their convolution, the different layers which they have will be able to represent. That is the convolutional filters they have at the different blocks. They are claiming those those blocks, they capture various features of clouds that are human interpretable. Unlike FMask and the method of 12, CloudNet is capable of learning both local and global features. It does not require any complicated pre-processing or superpixel segmentation. In addition, CloudNet effectively utilizes the extracted features from its sophisticated convolutional blocks to recover more accurate cloud masks. As a result, it delivers superior performance for cloud detection. Moreover, we have modified the dataset and so on. Okay. So fine. So let us come to the methodology. So this is what their network looks like. So basically, it's a like a sequence of convolutional layer, as you can see, and so they have convolution concat, that is concat means like that is where they concatenate the outputs of different layers, and max pool. uh, the bars with gradient shading represent the feature maps. So like these are basically what they have got at the feature maps which we have been talking about. These, according to them, these feature maps capture the cloud, the semantic features of the cloud. So yeah, so the details of that method of this method are present, and then like they are discussing their experimental setup. So let's look at their data set. So their data set like has 18 Landsat 8 images for training and 20 for testing. So I'm also 38 images are there total. So again, as you can see, the number of images is actually very low. But the thing is, these of course, it is based on only so few images. They cannot possibly train a neural network which has like millions of parameters. However, like what they will do is they will crop these images at multiple ways and use them for the training purpose. That is, they will basically decompose each of the images into patches and use for training. Therefore, instead of using automatically generated GTs of different training set, we use more accurate and manually obtained ground truths. This obviously affects the performance of the algorithm since the network learns the cloud features from correct images instead of inconsistent. Okay, so basically, so this is what their images inputs and outputs look like. So as you can see, this is a the image captured from the satellite, and corresponding to that, so these whitish regions, these are what where the clouds are located. So AE are the natural color images from the data set, and so then there are so B and F, these are the ground truths. That is, here these white pixels indicate that these are where the clouds are located, and the black pixels indicate no clouds. So here you can see large part of the image is covered by clouds, but in this case we see that only like the clouds are only in some small isolated pixels. And D and H are the results of their cloud net of what they have captured. Okay, so like we can see that, so this is the ground truth, and this is what their cloud detection algorithm is predicting. So you can if what to evaluate, we have to like see the precision of the cloud detection. That is, for we'll see how many pixels they are there which actually contain the cloud and have been predicted as cloud, and how many pixels have no cloud and have been predicted as no cloud. So that is the precision recall based analysis which evaluation which they do. So this is like a short and simple paper. And so again, this like if some like if you if some of you are able to get their code and data sets, you may be interested in just implementing this paper. Then, so then we come to another paper. So this is based on semantic labeling of aerial and satellite imagery. So what they are saying, so here, inspired by recent success of deep convolutional neural networks like CNNs and feature aggregation in the field of computer vision and machine learning, we propose an effective approach to semantic pixel labeling of aerial and satellite imagery using both CNN features and handcrafted features. Okay, so like yesterday I was telling you about handcrafted features, like say those filter outputs and so on. So as opposed to CNN features where like the filters are not created by humans, but they are the filter values are actually learned by the learned from the data by the optimization process. So they are claiming that they will be using the CNN features as well as the handcrafted features. Both CNN and handcrafted features are applied to dense image patches to produce per pixel class probabilities. That is, for every pixel, they will be attaching a probability of belonging to the different classes. Next, conditional random fields are applied as a post-processing step. So this is an important thing which they are talking about. The conditional random field, it's basically a probabilistic model. We'll understand what exactly it does. It infers a labeling that smooths regions while respecting the edges present in the imagery. So smoothness of pixels is something, or the spatial coherence of the pixels is something which I had told yesterday also. That is, if two pixels are adjacent, most likely they should be related to the same object. So that is so their labels should of adjacent pixels should be more likely than, or more often than not, they should be same level. However, that does not mean that it will always be the case. There are edges where like one pixel belongs to one class and another pixel belongs to another class. So basically, the what this CRF will try to do is that it will smooth the labels as far as possible. The combination of these factors leads to a semantic labeling framework which outperforms all existing algorithms on the ISPRS data set. So this is like a society of remote sensing which collects lots of these images and give them as a challenge to for these kinds of purposes. We advance state-of-the-art results by improving the overall accuracy to 88%. Okay, so let's go over this quickly. So in this paper, we apply CNNs to overhead imagery. We apply so this overhead imagery, they have considered different kinds of imagery. So note that this paper, the skyscapes, they dealt with RGB images, while this one they dealt with the images which they get from Landsat. I mean the at different these, so these are not RGB images. In this case they are saying, so they have different kinds of images. They have some cement color infrared imagery, CIR. Also have RGB imagery. So it's like they have on different times, they are proposing a framework which can work on different kinds of images. So what's the idea? Since overhead images are typically very large, computational efficiency is a priority. Second, by augmenting the training data with various transformations, the CNN representation can be robust to both translation and rotation. And since imagery could be captured at arbitrary azimuths, so azimuth is like a property of the satellites, the feature representation needs to be rotation invariant. That is, at whichever angle that is the same image can be taken at different orientations, or at different slopes and so on. So the features should not be affected by that. That is the complementary to learned visual features. We make use of simple handcrafted features proposed by previous submissions. Combining both CNN features and simple handcrafted features slightly boosts the performance accuracy. Now, as a post-processing step, a CRF, a conditional random field, is applied to the label probabilities. So the CNN, this will give you the for at every pixel, it will give you the probabilities of that pixel belonging to the different classes. So now what they will do is this CRF is applied to the all these to the probabilities at every pixel, And what it does is it infers a globally consistent labeling that is locally smooth except at the edges of the imagery. So this is what I said, like the labels should be locally smooth. That means apart from the edges, where there is a change from one object class to another, it should, within the edges there should the pixel should be like consistent with, I mean the pixel levels should be consistent with each other. In the previous work on the ISPS channel, the superpixel CRS were found not to increase the accuracy. Where in this paper, we use a pixel level CRF to avoid the errors in over segmentation. That means, so over segmentation means like you like each pixel. It's like you go to the segmentation at unnecessary or irrelevant details. That is like, so say for example, if you are considering several pixels which belong to a, say a car, then even within the car, the say let us say the pixels belonging to the window of the car and the pixels belonging to the body of the car, they will like they will have different intensity values, right? So like like a very fine grained separate segmentation, it might segment the windows of the car as some as one group, the body of the car as one other group, etc. So that is like over segmentation. We do not want that. We want the car as a whole, which includes the body as well as the windows. So this kind of over segmentation is prevented with the help of the CRF that they are talking about. Okay. So pixel classification with a convolutional network. So they show how the CNN will do the pixel wise classification. So this is their formula. So they take the image as the whole. Now they extract the windows in the image. So as I am saying repeatedly, it is, instead of focusing on the full image, you have to take the various patches of the image and like run your and provide those patches as the inputs to the whatever model you are building. So at patch level, your CNNs will create this probability distribution. So and then the same pixel can be part of multiple patches. That is like we can consider a patch like this, we can consider another patch like this. So the windows are sliding, so like the same, and so there will be overlap, and in each case different pixels will be getting the different probability, like each pixel will get a probability distribution over the different labels. So when the window is placed here, maybe this pixel will get one probability distribution. But if the window is slightly moved, maybe it will get another probability distribution. So then, on the other hand, when they are going for the handcrafted features, maybe they again the each pixel will get probability distribution over the levels. So then we have, for every pixel, we have so many different probability distributions. Then based on which may be contradictory to each other. So based on this, what is the final prediction we can make? So that is what is achieved by this probability model called the conditional random field. So what exactly the conditional random field does is like is beyond the scope of this discussion. But basically, you can say that given a test sample xt and learned weight vectors, the probability that the sample xt belongs to a particular class is given by a particular formula. So so it is doing so pixel level prediction. So for every pixel, so each like this xt is basically talking about one particular pixel, which now that is so that is represented by the all its features, right? For every pixel I have all the like all different kinds of features which may be either the CNN features or the handcrafted features, everything all arranged in the form of a vector. So this xt, this is the feature representation of the pixel, and then there are weight vectors which it itself which the CRF itself calculates. So based on that, it will like calculate a probability distribution over the different labels. And in doing so, it will consider the relation between the different pixels. So it's a graphical model. This CRF, conditional random field, it's a graphical model. So what is meant by a graphical model? It's like it considers each example as nodes in a graph, and those examples which are neighboring, they are joined by an edge. So and their corresponding labels are also joined by an by edge. So which makes that whenever two things are joined by edge, those like this CRF has a property is such that whenever two nodes are joined by an edge, it tries to make sure that the nodes joined by the edge, they have the same value. So if there are two adjacent pixel whose label nodes are connected by an edge, most likely both of them will get the same value. So that is what is achieved with the help of the CRF. Okay, so basically that's what they do. So they here they have discussed the convolutional neural networks. So they have to calculate the CNN features. So for that they have different kinds of CNNs. So, and they do it at different resolutions. So like they or rather, as I said, they have different patch sizes. So they have them 16 cross 16 patches, 32 cross 32 patches, 64 cross 64 patches, etc. So for each of these patches, they provide as inputs to CNNs, and they, as a result from those all those CNNs, they get the feature maps. So it's like for any particular pixel, they get different feature values from the different feature maps, and those feature values are all concatenated and fed to a classifier. Okay, and then so basically based on this we can do the like this is what like a particular one CNN architecture may look like. So in this case, the network input is 64 cross 64 cross 3. So as I said, there are 16 by 16, 32 cross 32, and 64 by 64. So this one is shown for the case of 64 by 64. And uh, yeah, so the 64 by 64 are normalized DSM images. So that's a particular category of image. The network consists of 6 layers, so which are 4 convolution. So these are the convolution layers, and 2 fully connected layers. So these are the FC fully connected layers with a 5-way softmax layer. So basically each thing is to be classified into 5 possible classes. So that is why they like we get a 5-way softmax layer. That is, it's like basically a probability distribution over 5 classes. So this output layer, it will contain the probabilities of the different classes. So we have a 5-layer softmax. Okay, so and then so this is the output we get from the CNN. So each CNN is at every pixel provides you this kind of a uh, like a probability distribution, and then these probability distributions are passed on to the to our this thing to the CRF. So also they are saying that they build something like a random forest classifiers also, which like this is maybe I mean this is something which they have done. I mean usually CNN and random forest usually don't go together, but whatever it is, so basically, they are what they are saying is that they get different probability distributions from like maybe from different versions of the CNN and other classification algorithms, and then they get a combined probability distribution by that is from different probabilities. They like take a like take some kind of average, and they come up with a combined probability distribution for each of the pixels. Next, what happens is CRF is a probabilistic graphical model that has been used. Okay, so what the CRF will do is it will take the probability distributions for every pixel. It will also take in the features, the image features of every pixel, the feature representation, as well as the graph structure. That is, a four connected grid in which every node corresponds to the class level of an image pixel. So basically every pixel is connected, that is we in the CRF it's a graphical model, which means that for every pixel we have a node, and then we have edges between the neighboring pixels. So and then based on that, like the pixel, the CRF is able to get the this thing. Okay. So yeah, so this is what the edges. So they can get the edges from different sources. So this is the original image. So so if they do some kind of an edge detection method on the image, these are the different edges they can get. But they can also get these kinds of edges by not only from this image, which may be from the visible domain, visible range, but also from other versions of the same image. I mean, maybe the like a CIR image is available, or maybe there is something known as NDVI, or some vegetation index, normalized vegetation index can be calculated. That's also based on some the satellite imagery only. So it's like for the same region we can get an image around like we can get different kinds of images, and each kind of image can be processed and a set of edges can be found out like this. Then what the CRF will do is like or what the CRF will implicitly do is that it will like combine all the like it will produce such an image which has like the which combines all the image edges, and this is what that combination may look like. So after that, they have gone into the data set. So they have discussed what is the, like again, they have got 33 large image patches. And then from, so in total, there are 168 million pixels. Okay. So the different, so they have mentioned that they have about 33 images, and from each of the images they get like about 5 million pixels. So that total there are 168 million pixels, and for each of the pixels are going to be labeled. And so like these are the 5 or 6 categories into which they are doing the classification. And so like basically the whole thing is explained how they do it, and the results are for each of the different approaches for each category. So there are 5 categories: the surface, building, the low vegetation, trees, and cars. So like they were earlier talking about these 5 dimensional probability distribution. So these are the what they the levels that they correspond to. So so then for each of the classes they have shown the accuracy, that is, or maybe the precision, and they have just shown how to which approach gives performance in which thing. So yeah, so they have also shown the different the different image sources. One is the ortho, that is the standard RGB imagery. Then orthophoto plus DSM, some raw digital surface model, and then the normalized DSM. So like all these, so these are basically the different types of images which they have acquired from the using the remote sensing. And and as they were showing here, the each of the different images will give a different set of edges or different probability distributions for the pixels, so they can be combined. And so this is the result of such combination. And so these are some of the segmentation results which they are showing. Okay, fine. So that's what this paper does. I will briefly look at 2 other papers. So what this paper does is a framework for large-scale mapping of human settlement extent from Sentinel-2 images via fully convolutional neural networks. So just like Landsat, Sentinel is another satellite from which images are available, at free of cost. I mean, maybe not fully free of cost, but like it's you may have to do some registration, but it's possible to easily get these images. Now, I mean, they are publicly available. So what these people are doing is that human settlement extent information is a valuable indicator of worldwide urbanization as well as the resulting human pressure on natural environment. Therefore, mapping HSE is critical for various environmental issues at local, regional, and even global scales. This paper presents a deep learning based framework to automatically map HSE from multispectral Sentinel-2 data using regional available geoproducts as training levels. So it will take a multispectral image from this Sentinel satellite and map it to the HSE map. So I will show you examples of that in a bit. So a straightforward, simple, and yet fully convolutional network-based architecture sent to HSE is implemented as an example of semantic segmentation within the framework. The framework is validated against both manually checking or manually labeled checkpoints distributed evenly over the entire test areas and the OpenStreetMap building layer. So Google OpenStreetMap you may have heard of. So like they actually give maps of the at street level, like including the buildings. I mean the buildings are annotated in this OSM. So whatever they have, whatever like human settlement they have identified, they are to be validated against this OpenStreetMap. So basically it is expected that they will be able to segment the image or identify the structures at till the street level. The HSE mapping results were extensively compared to various baseline products in order to thoroughly evaluate the effectiveness of the proposed HSE mapping framework. The HSE mapping power is consistently demonstrated over 10 representative areas across the world. We also present one regional scale and one countrywide HSE mapping example. Okay. So they have done it at like at a very regional scale, maybe at a state level or city level, and once at a country level, to show that like at different resolution they are able to do this segmentation. Okay. So let's skim through this paper quickly enough. Mapping with the Send2HSE net. So considering the spatial resolution of available reference data at 20 meters. So as I am saying, the satellites currently is capable, I mean every pixel of a modern satellite will be the edge of every pixel will be of size in a few meters, that is 20 meter in this case. The sub-pixel geolocation accuracy of Sentinel-2 data, which is 20 meters. The specific goal of HSE mapping in this study is to detect whether buildings, roads, and other man-made structures are presented. That is larger than 0% in a 20 cross 20 cell. So every pixel is like a 20 meter by 20 meter region. So whether that 20 meter by 20 meter region, whether it contains some buildings or roads or other man-made structure. Okay, I mean, so total 400 square meters is there. So out of these 400 square meter region, is there even like some region more than zero? I mean, some non-zero region which covers any of these things. That is what they are trying to do. Okay, so using this definition, the resulting HSE output from Sentinel-2 imagery will be a binary layer in the in some coordinate system with a ground sampling distance of these 20 meters. Okay, this definition is also consistent with a like a global human built-up and settlement extent. So this is some other data set which they have got from the Landsat imagery. So this is being done from one satellite, Sentinel, and they are comparing it with the similar data set obtained from the Landsat image satellite which we talked about earlier. Okay. So like basically this is what it looks like. So this is, like you can see, this is the sentinel image, and this is the like HSE reference. That is, the red indicates those pixels which contain built up areas, and and these white are the white are the those pixels which do not contain the built up areas. So that's what they do. They basically, the input to their whatever neural network they are developing, the input will be like a map like this captured from the Sentinel satellite, and their output will be this kind of a binary image where uh, for every pixel the value will be either 1 indicating that it contains some built up area, or 0 indicating that it does not contain any built up area. And their aim is to train the model for certain regions in Europe, where so Europe is like a very developed place, so where a lot of reference data is also available, maybe at pixel level, say in things like, say, Google OpenStreetMaps and things like that. So they have a very detailed ground truth about which pixel actually contains some built up structure and which pixel doesn't. So they will utilize this the European data which contains a lot of these labels. So they will train the model in the data rich region of Europe and then test it in data poor regions which are beyond Europe. Okay, so this is what the image their neural networks looks like. I mean, this is a fully convolutional network. So as you can see, it just, there are no skip connections or any other kinds of complicated things. It's like a sequence of convolutional steps. There is like, and then there is one max pooling level followed by again some convolution steps, and finally you get the output. Okay, so this is what is called an FCN, a fully convolutional neural network. So, after that, they have given the details of the experiments. I'm not going into those details. So you can easily access these papers and take a look at them. And finally, one more thing which I just wanted to skim through today: building detection in VHR's SAR images. So very high resolution, like synthetic aperture radar images. So these are the typical satellite images which we get from the in remote sensing using fully convolutional neural networks. So this is also, this is also, the target is very similar to this paper. So here they were looking for built up areas, and here they are specifically looking at buildings. So this paper addresses highly challenging problem of automatically detecting man-made structures, especially buildings, in very high resolution synthetic aperture radar images. In this, the paper has two contributions. First, it presents a novel and generic workflow that initially classifies the spaceborne SAR tomographic point clouds which are generated by these images. So this is related to more to do with the processing of the images and less about the interpretation. Uh, that is that they are calling as their first contribution into buildings and non-buildings with the aid of auxiliary information, such that either using openly available 2D building footprints or adopting an optical image classification scheme. So just like these guys talked about uh, these that is the auxiliary data from the other sources such as OpenStreetMaps. Here also they are talking about other data sources. And second, these labeled data sets have been utilized to construct and train a state-of-the-art deep, fully convolutional neural network with an additional CRF. So once again, we are coming back to the concept of CRF, represented as a RNN, to detect building regions in a single VHR SR image. Such a cascaded formation has been successfully employed in computer vision and remote sensing fields for optical image classification, but has not been utilized for this kind of imagery. So it's like just a recapitulation of all the concepts once again. They have the only thing is that they are doing it on a different kind of image, the VHR SAR image. So this is what the visible spectral image, or or what they are calling it as the optical image Google is looks like. This is like And this is like a simple RGB image in the visual spectrum, I mean in the visual range taken from above. But for the same geographical region, if the VHR SAR image is taken from a satellite, this is what it looks like. So as you can see, there is there is not much similarity. But these green polygon like things which you are seeing, these are actually the buildings which have they want to detect. So in this image, from by looking at the, so you can understand that this is like the rooftop of a building of this is one another one. Similarly, there is another high-rise building here, and this is its rooftop. So these are the buildings which it wants to detect. So it is one thing to identify these rooftops in this visible range image, but if they look at this VHR SAR image, it does not look like that at all. That is, a human looking at it will not be able to understand it. So here the challenge is to build some kind of a model which will be able to take this kind of an image as input and identify the relation between the pixel values in this image and the classes, the buildings which we are interested in. Okay. So based on that, they have proposed a neural network whose details is given here. So this is also a fully convolutional neural network. That is, there are only convolutional layers and pooling layers. It's a U-Net kind of thing because there are some like upsampling also. This done through deconvolution. And then they have also used the CRF, the conditional random fields, for that same purpose as said earlier, just to that is for every pixel. So the neural network will make some kind of prediction at every pixel, but then we know this information that that adjacent pixels are likely to belong to the same class, that is building or non-building. So that kind of that label smoothing between adjacent pixels, that is achieved with the help of the conditional random field. So additionally integrate binary potentials, just yeah, to additionally integrate binary potentials, we add a CRF represented as an RNN. This gives us an end-to-end trainable network. So in general, the CRF is not a neural network, but they are like mixing the convolutional neural network and the CRF. So the CRF will have its own parameters which have to be learned, and the neural network will also have its own parameters to be learned. So instead of doing the two things separately as was done in this paper, so here what these guys are doing is that they are integrating the CRF with the neural network itself by representing somehow the CRF as a recurrent neural network. So they are using some paper which does that kind of a thing. Now, in detail, the first part of our network calculates a feature for each input pixel. Therefore, we exploit a FCN with in-network upsampling and skip and fuse architecture to fuse coarse, semantic, and local and appearance information. So that is, they have got the pixel representation, and they may also have some auxiliary information from the other sources. As we are exploiting FCN, we exploit the ability of to not only classify a single pixel but also perform image segmentation for images of arbitrary size at once. The second part adds the binary potential. This means that it adds constraints to give neighboring pixels with a similar intensity the same level. This is what I was mentioning. So this is the pixel level smoothness which they try to enforce with the help of the conditional random field. Okay, so that is so like all these concepts we have seen in the previous papers also. So like they all so this paper brings all of them together. But the novel thing about this paper is that this does it on the VHR SAR images. So as I said, like just by looking at a VHR SAR image, you will not get any, or you'll not be able to form any particular idea. So that is by just by looking at it. So this is an image over the city of Berlin. Just by looking at this imagery, will with your eyes, you may not be able to get form any idea about which region, like which pixels contain a building or something like that. It is like that's because our eyes see at one frequency or and like these or at one wavelength, and these like at a different part of the spectrum. So the challenge is to map this spectrum, I mean this part of the spectrum, to the semantic concepts like building that we are looking for. So that is what that is what this paper aims to do. Okay, so that brings us to the end of today's class. So basically what we did is we discussed a number of papers, a number of example papers where we see how to use various deep learning techniques or neural networks to on satellite imagery or aerial imagery to identify structures which we may be interested in, either identify specific structures like buildings or roads or built up areas, or to do the semantic segmentation of the image, or even things like cloud removal. So like each of these papers, I mean like you can reference each of them, you can search them, you can look at the references, and if any one of you are interested in a project to on this topic, like I hope you have given the